incoming! Get down! Mortars! Take cover! Medic!
Power levels are unstable.
Adjusting the primary lens stabilizer.
There. Holding steady at maximum intensity.
This configuration isn't working. The signal is too weak.
What if we amplify the reflection angle here? It might stabilize the readings.
January 17th, 1943. The night is absolute. A freezing wind cuts across the darkened fields of North Africa. Sand and debris swirl in the dim moonlight. Somewhere ahead, a group of American soldiers crouches behind a ridge, rifles poised, eyes straining into the black. They cannot see their enemies. Shadows shift. Every sound, a distant shuffle, the snap of a branch, sets hearts pounding. Mortars explode in the distance, brief flashes illuminating terrified faces for a split second, then plunging them back into darkness. In these hours, the battlefield is a cruel game of guesswork. Soldiers fire blindly, hoping their aim will meet the unseen. Casualties mount. Frustration grows. Commanders know their men are at a stark disadvantage. Yet, in the midst of this night, a small team in a laboratory far from the front lines is tinkering with a device that could change everything, a way to pierce the darkness, to see what no eye could ever detect. A glowing promise in a black world. This is the story of how America learned to fight the night. By 1943, World War II had engulfed the globe for nearly 4 years. On the battlefields of Europe, North Africa, and the Pacific, the nights were as deadly as the days. Darkness was no friend. It was a silent enemy, turning every patrol, every raid, into a game of chance. Allied soldiers faced ambushes they could not see coming, and even routine operations carried the risk of death. Night combat was limited, crude, and terrifying. Infantry relied on flares, lanterns, or rudimentary tracer rounds, each method with its own deadly flaw. Flares exposed positions. Lanterns were slow and cumbersome. Tracers, though visually helpful, marked the shooter as easily as the target. Even tanks, armored vehicles, and artillery units struggled. Targeting in the dark was a gamble. Fires, explosions, and fleeting silhouettes were all the information a soldier had. Success often depended on luck, instinct, or the enemy's mistakes. Meanwhile, the Axis powers had begun experimenting with night fighting technology. German engineers had developed the Vamper system, a crude infrared rifle attachment that allowed infantry to detect enemies in darkness at short ranges. By 1942, some German units were already field testing infrared scopes on the Eastern Front. Night patrols using Vamper allowed German soldiers to ambush Allied forces with terrifying efficiency. The mere rumor of these capabilities spread through Allied ranks, creating both fear and determination. The United States, however, lagged behind. American soldiers at Kasserine Pass in Tunisia and other theaters quickly discovered the limitations imposed by darkness. Commanders reported missed opportunities, unnecessary casualties, and operational paralysis after sunset. Equipment planners, armored corps officers, and infantry commanders alike recognized the need for a technological edge. The military bureaucracy, slow as it could be, acknowledged the gap. The U.S. Army Signal Corps, responsible for communications and electronics, began exploring ways to adapt existing technology for battlefield use. By late 1942, they were aware that simply throwing more flares or night patrols at the problem would not suffice. A solution would have to be both mechanical and optical, capable of giving soldiers the ability to see at night without exposing themselves. Enter the Sperry Gyroscope Company. Known primarily for stabilizing instruments, naval gimbals, and analog computing devices, Sperry had earned a reputation for engineering precision. The Army approached them with a simple but urgent challenge. Invent a device that could see the unseen, a way to make night visible. It was no small task. The technology did not exist in a practical, portable form. Electronics were bulky, batteries limited, and optical systems prone to distortion. Despite these hurdles, Sperry engineers began work in earnest. Laboratories in Brooklyn hummed with experiments. Infrared lamps, photocells, and prototype lenses were tested under simulated battlefield conditions. Engineers worked around the clock, driven by the knowledge that their device could save countless lives. Meanwhile, Army officers studied German reports, dissecting photographs of the Vamper system and examining capture prototypes. They measured range, luminosity, and field of view. Every observation pointed to a daunting truth. Night combat would remain a deadly gamble until technology could intervene. By early 1943, it was clear the U.S. needed innovation on a compressed timeline. Every month of delay could cost lives and hinder offensives in North Africa, where the Allies were already pushing toward Tunisia against entrenched Axis forces. The clock was ticking. Darkness was relentless, and the battlefield would not wait. The need was urgent. Soldiers' lives hung in the balance, and command demanded a solution. A new frontier of warfare was emerging, one where the ability to see at night could tip the scales between victory and defeat. And so, Sperry embarked on a race against both the clock and the unseen enemy, laying the foundation for a technology that would change night combat forever. This relentless pursuit of innovation leads directly into the next chapter. The deeper exploration of Sperry's work, the science behind infrared, and the first American attempts to pierce the night. By mid-1943, the United States Army was confronting a stark reality. Conventional weapons and tactics were insufficient for night operations. In North Africa, night raids on German positions often ended in chaos. Patrols stumbled over unseen obstacles. Mortar fire hit nothing but the desert floor. Soldiers returning from missions described ghostly shapes and flashes in the darkness, yet the enemy remained elusive. Casualty reports confirmed the growing toll. Leadership understood that daylight advantages could not offset the lethal limitations imposed by nightfall. Sperry Gyroscope, tasked with solving this problem, approached night vision from a methodical, engineering perspective. Unlike conventional optics, which relied on reflected light, the goal was to detect infrared radiation, heat emitted by bodies or engines. Early laboratory experiments involved massive lamps, crude sensors, and lenses that could barely focus images in a darkened room. Engineers confronted the physical limitations of the era. Vacuum tubes were fragile and energy-hungry. Photocells were slow and inconsistent. Batteries could barely sustain the devices long enough for meaningful use. The first American prototypes were bulky. One unit resembled a cumbersome rifle-mounted box with wires snaking to a backpack-sized battery. The optics magnified faint infrared light, producing a ghostly, blurry image on a small screen. Testing these devices in simulated night environments revealed both promise and frustration. Soldiers could detect shapes at short range, but accuracy was poor. Any misalignment rendered the scope useless. Dust, smoke, or fog further reduced visibility. Yet, even in these early trials, a glimmer of hope appeared. Night could, in theory, be tamed. Meanwhile, military planners were acutely aware of the strategic implications. Night had always been a sanctuary for infiltration, ambush, and retreat. If the United States could overcome this darkness, entire operational paradigms could shift. Engineers and officers studied German successes, particularly the Vamper system deployed on the Eastern Front. Though limited, effective only at tens of meters, the Vamper demonstrated the potential of infrared warfare. Captured documents and first-hand intelligence indicated that German infantry equipped with these scopes could dominate nocturnal skirmishes, inflict casualties with precision, and move with impunity. The Army's leadership pressed for accelerated research. Funding increased. Prototype iterations multiplied. Sperry engineers worked closely with the Signal Corps, sharing findings, adjusting optical configurations, and testing new infrared lamps. They experimented with vacuum tube sensitivity, filter coatings, and lens alignment, seeking a balance between size, weight, and clarity. For the first time, the U.S. began to see the contours of a viable combat solution. At the same time, practical field challenges loomed large. The scopes had to function in desert heat, jungle humidity, and the freezing nights of Europe. They had to survive jostling in vehicles, recoil from rifles, and the rough handling of soldiers in combat. And they had to be intuitive enough for troops with minimal training. Every engineering choice was a compromise between theory and battlefield reality. By late 1943, the first operational prototypes were being tested by select infantry units and armored divisions. Soldiers were skeptical. A corporal in Tunisia described the initial trials as like trying to peer through a foggy window while running. Still, reports noted that with practice, detection rates improved. A distant figure moving under moonless skies could be spotted, if only as a pale silhouette against the terrain. The technology had not yet solved all problems, but it represented a revolutionary step forward. These experiments also highlighted a critical psychological effect. For the first time, soldiers began to realize that darkness was no longer absolute. The terror of unseen enemies could be mitigated, if only slightly. Confidence grew, and the concept of night combat evolved from pure survival to a potential tactical advantage. The battlefield, once dominated by uncertainty, was beginning to bend to human ingenuity. As Sperry refined lenses, photocells, and battery systems, the stage was set for the next phase, examining the same problem through multiple angles, human, tactical, technological, and enemy, to understand why infrared night vision would transform the war. Each perspective revealed a different facet of the challenge, highlighting not only the mechanics of invention, but also the human cost of fighting in darkness. Night combat in 1943 was a crucible of fear and uncertainty. Soldiers faced not only the enemy, but also the oppressive weight of darkness itself. Eyes strained against shadows, every movement amplified, every sound magnified. Reports from North Africa describe infantrymen freezing mid-step, unsure whether a distant rustle signaled an enemy patrol or the wind sweeping through sand dunes. Casualties were often the result of misidentification or blind fire, not enemy skill. Beyond immediate danger, the psychological toll was severe. Letters home spoke of nights that never end and walking ghosts. Training could only go so far. No amount of drills could prepare a man for the terror of firing into blackness while knowing the enemy could see him, but he could not see them. Night brought a distinct sense of vulnerability. Officers recognized that morale and effectiveness suffered after repeated failed night operations. Soldiers expressed frustration, despair, and at times, fatalism. It was not just the physical battlefield that was unforgiving, but the mental one as well. The human stakes created urgency. If a device could grant vision in the dark, it would not merely improve accuracy. It could save lives, restore confidence, and turn nights from a time of terror into a tactical advantage. Sperry's experiments were not theoretical. They were a direct response to the anguish of men on the front lines. Every prototype carried the weight of human survival. The challenge of creating night vision in 1943 was monumental. Conventional optics relied on ambient light. In the absence of moonlight or flares, soldiers were effectively blind. Infrared technology promised a way to detect heat signatures instead of relying on visible light. Yet early American engineers confronted the harsh realities of physics and wartime logistics. The Sperry prototypes were intricate and fragile. Infrared lamps emitted invisible light, while photocells translated that radiation into an image on a small cathode ray screen. Lenses had to be precisely aligned. Any misalignment caused distortion or complete failure. Batteries were bulky, limiting mobility and duration. The first units weighed dozens of pounds and required careful handling. Even slight vibration could render the scope useless. Moreover, environmental factors complicated matters. Dust, sand, fog, or smoke could scatter infrared signals. Bright explosions could temporarily blind the sensors. Engineers continuously refined materials, coatings, and circuits, seeking balance between performance, durability, and portability. What eventually emerged was a portable infrared scope, still primitive by modern standards, but revolutionary for its time. Every component represented years of accumulated knowledge in optics, electronics, and engineering. The ingenuity lay not only in making the device work, but in making it usable by soldiers in the chaos of combat. Sperry's success was as much a triumph of applied physics as it was of battlefield necessity. The lack of night vision fundamentally altered military strategy. Darkness favored the defender, the ambusher, and the patient sniper. Allied units without infrared capabilities were constrained in their operations. Night attacks, reconnaissance missions, and flanking maneuvers carried higher risk, often canceled or postponed. Armored divisions struggled to identify targets after sundown, leaving tanks vulnerable to enemy fire. German forces, with limited infrared equipment, could exploit these vulnerabilities. Even when only a few Vamper-equipped soldiers were deployed, they created disproportionate disruption. The Allies, in response, relied on illumination rounds, tracer fire, and flares, tools that revealed positions as much as they revealed enemies. Commanders faced a grim calculus: advance under darkness and risk ambush, or halt until daylight, sacrificing momentum. The development of American infrared scopes promised a radical shift. Units equipped with night vision could conduct raids with precision, detect ambushes before encountering them, and maintain the initiative during darkness. Potentially, battles could be fought on the soldiers' terms rather than under the tyranny of the night. This tactical advantage was not hypothetical. Field trials and control conditions showed that even limited visibility gains dramatically improved target acquisition and reaction times. Night would no longer be an equalizer. It would become a domain where technology could tip the scales, transforming a previously chaotic battlefield into one shaped by strategy, training, and innovation. The Germans were the first to grasp the tactical potential of night vision. By 1942, they had begun deploying the Vamper infrared rifle system on the Eastern Front. It was crude, cumbersome, and limited to short-range engagements, but it worked. German infantry equipped with Vamper could detect enemy movements in complete darkness, transforming ambushes into lethal encounters. Even a handful of Vamper-equipped troops created significant disruption. Allied patrols reported sudden, precise bursts of fire from invisible enemies, followed by silence. The psychological effect was profound. Fear of unseen adversaries slowed advances, eroded confidence, and forced changes in tactics. Reconnaissance and night raids became risky propositions. German engineers, in this way, achieved more than a technological milestone. They weaponized fear. Captured prototypes and intelligence reports highlighted the stark contrast between American and German capabilities. U.S. troops were essentially blind after sunset, relying on crude flares or guesswork, while the Germans could operate with a degree of certainty. Recognizing the gap, U.S. military leadership moved decisively, albeit through a bureaucracy that was often slow to act. The Army Signal Corps coordinated with Sperry Gyroscope, emphasizing research that could produce practical, deployable units. Officers tasked with procurement and development understood the stakes. Inaction could cost lives and operational momentum. General officers overseeing North African campaigns pressed for accelerated timelines. Reports from Tunisia, Libya, and the Mediterranean theater detailed repeated failures in night operations and growing casualties. Leadership demanded a solution not as a theoretical experiment, but as an urgent operational necessity. This collaboration between engineers and commanders exemplified wartime problem-solving at its best. Officers communicated real-world needs. Engineers translated those requirements into mechanical and electronic solutions. Testing schedules were accelerated, prototypes modified based on field feedback, and training programs designed to integrate infrared scopes into actual infantry operations. Every decision, from design tweaks to deployment plans, reflected the urgency imposed by darkness on the battlefield. Beyond tactics and technology, night vision touched deeply on the human psyche. Darkness magnifies fear. Soldiers in 1943 often described night as a living entity, concealing threats that could strike without warning. Missed shots, confusion, and disorientation fostered helplessness. Morale declined when men felt powerless in the dark, even if heavily armed. The promise of infrared technology offered more than a mechanical advantage. It offered psychological relief. Even early prototypes, with blurry displays and limited range, instilled confidence. The knowledge that an unseen enemy might now be seen, before it could strike, change behavior, Patrols became bolder, night operations more feasible, and soldiers' trust in leadership and equipment strengthened. Yet the psychological aspect cut both ways. Soldiers had to learn to interpret the ghostly images on infrared screens, a skill requiring training and patience. Early misreads could provoke panic or hesitation. Commanders emphasized repetition and drills to build familiarity. Over time, as scopes improved, the technology not only leveled the tactical playing field, but reshaped the emotional landscape of nocturnal warfare. By late 1943, Sperry's infrared prototypes were ready for controlled field trials. The laboratory experiments in Brooklyn had proven the concept. Heat could be converted into visible images. But the true test awaited under the unforgiving conditions of war. In North Africa and the Pacific, darkness was absolute. Sand, mud, smoke, and sweat conspired against the untested technology. The question remained, could it function outside a laboratory in the chaos of combat? The first American tests were modest. Small infantry units, carefully selected and trained, were issued the earliest infrared scopes. These rifles were cumbersome, boxes of electronics mounted above the barrel, wires trailing to a heavy backpack battery. The operators moved slowly, cautious of their own weight and the device's fragility. At the test range, they faced targets in total darkness, shadows blending with the desert night. At first, failure was common. Images flickered, and tiny movements could throw the entire view out of alignment. Soldiers struggled to interpret the ghostly silhouettes on the small screens. Some abandoned the devices after only a few attempts, frustrated and exhausted. But the engineers and trainers were relentless. Adjustments were made, lens positions fine-tuned, battery voltage stabilized, filters replaced. Each small improvement increased clarity, range, and reliability. By December 1943, a breakthrough emerged. Under moonless skies, a soldier could detect a figure at 30 to 40 meters, enough to identify movement, not yet to aim with precision. For the first time, darkness no longer equaled helplessness. Observers noted trembling hands steadying rifles, eyes straining with anticipation rather than fear. What had seemed like a fragile experiment was slowly becoming a practical tool. Simultaneously, the Signal Corps tested mobile applications. Vehicles mounted with infrared spotlights and detection units allowed crews to monitor roads and perimeters at night. Armored scouts reported that early infrared could identify enemy positions, trenches, and even vehicle movements, albeit imperfectly. The combination of rifle-mounted and vehicle-mounted systems suggested a future in which night operations could be coordinated and effective. The human dimension of these tests was significant. Soldiers initially skeptical or fearful began to embrace the technology, reporting increased confidence during night maneuvers. For the first time, the U.S. Army could consider proactive night patrols rather than defensive postures. Trainers emphasized discipline. Operators learned to read the faint silhouettes, recognize false positives, and adjust quickly. Experience and repetition transformed a crude prototype into a functional battlefield tool. Yet operational limitations remained. Battery life was short, image resolution low, and the devices were prone to failure in sandstorms, humidity, and after repeated recoil. Engineers documented each issue meticulously, knowing that incremental improvements were key. These field trials, though imperfect, provided critical data. Without them, mass production or deployment would have been impossible. The stakes were clear. Night raids, ambushes, and reconnaissance depended on these early devices. Even partial success promised a strategic edge over an enemy still relying on conventional night operations. Every test, every malfunction, and every small victory brought American soldiers closer to seeing what had been invisible, gaining the initiative when the sun had set. This period marked the first tangible turning point. Sperry's infrared scopes had moved from theory to action. Soldiers were no longer wholly blind after dark. Engineers understood the limitations. Trainers prepared operators. Commanders began to see tactical applications. The battlefield had begun to shift, not immediately, not perfectly, but irrevocably. These initial breakthroughs paved the way for more extensive trials and full-scale deployment. The technology was fragile, yet revolutionary. From laboratories to desert testing grounds, the U.S. had begun to wrest night from the enemy's advantage. By early 1944, the U.S. Army had scaled up its night vision trials. Infantry companies, previously equipped with only a few prototypes, were now receiving multiple units for coordinated exercises. Engineers, officers, and selected soldiers gathered at remote training grounds in the deserts of North Africa and the hills of the American Southwest to simulate night combat conditions. The goal was clear: determine whether infrared technology could function reliably under stress, uncertainty, and motion, conditions soldiers would face on the front lines. The exercises were rigorous. Teams advanced through pitch-black terrain, encountering mock enemy positions, obstacles, and intermittent illumination from control flares. Operators mounted rifle scopes, while spotters monitored vehicle-mounted infrared units. Early tests had revealed weaknesses: battery life, lens distortion, and sensitivity to dust, but repeated trials allowed the teams to adjust. Soldiers learned to anticipate the flickering images on the small screens, to distinguish human silhouettes from environmental noise, and to coordinate movement based on ghostly shapes barely visible in the infrared spectrum. One notable trial involved a simulated ambush scenario. Infantrymen equipped with the new scopes moved along a narrow ridge, while instructors and observers posed as enemy combatants. At first, movement was cautious and tentative. Operators misread shadows, reacted to phantom signals, and hesitated to fire. But after repeated runs, soldiers began to detect the enemy before being seen themselves. Silent communication, hand signals, and careful alignment of scopes allowed them to execute coordinated maneuvers with unprecedented confidence. For the first time, darkness no longer guaranteed vulnerability. It could be leveraged as a tactical environment. Engineers documented each moment. Battery drain rates, lens stability, and sensor accuracy were logged meticulously. Every failure led to immediate adjustments, reinforcing wiring, improving insulation against heat and humidity, and refining lens calibration. By mid-trials, the scopes could reliably detect human-sized targets at 30 to 40 meters, while larger obstacles and vehicles were visible at greater distances. Though far from perfect, these advances proved the fundamental principle. Night vision was possible, practical, and potentially decisive. Commanders observed another critical effect: morale. Soldiers previously hesitant to advance under darkness displayed greater boldness. Teams could perform reconnaissance, flank maneuvers, and security sweeps with measurable success. Even simulated artillery targeting became more precise, as infrared operators could track movement and signal coordinates in real time. These exercises transformed theoretical capability into practical battlefield skill. Field demonstrations also highlighted limitations, which informed production priorities. Devices remained heavy and cumbersome. Batteries were still short-lived, and accuracy required intense training. Engineers considered these challenges opportunities rather than setbacks. Each prototype provided data to refine designs, improve optics, and extend operational life. Soldiers, in turn, became increasingly comfortable, developing muscle memory and visual intuition for interpreting infrared images under combat stress. By the conclusion of these trials, Sperry and Army leadership had a clear picture. Infrared night vision could be integrated into combat units, albeit with careful deployment and ongoing refinement. The gap that had haunted American soldiers in 1943, blindness under darkness, was narrowing. For the first time, the U.S. had a tangible solution that could rival and potentially surpass the German Vamper system. The significance of this success extended beyond mere experimentation. It represented the first moment in American military history when night combat could be approached proactively. Previously, darkness had dictated strategy. Now, technology allowed commanders to dictate tactics even after sunset. Soldiers could advance confidently, observe enemy movements, and act on information previously inaccessible. Infrared was not just a tool. It was a psychological weapon, shifting initiative and expectation in favor of those who wielded it. These trials marked the climax of America's night vision story in 1943 to 44, a transition from blind vulnerability to controlled observation, from tentative experiments to validated operational capability. The battlefield was no longer absolute. It could be navigated, understood, and even dominated under the cover of darkness. By mid-1944, Sperry's infrared scopes had moved from experimental trials to limited deployment. Production, though modest by later standards, reflected a serious commitment. Hundreds of units were manufactured, each carefully calibrated and tested before being issued to selected infantry, reconnaissance, and armored units. The U.S. Army sought to place these devices in the hands of soldiers operating in environments where night engagements were frequent and daylight advantages minimal. The impact was immediate if measured. Units equipped with the scopes reported increased confidence during night maneuvers. Patrols could detect enemy movements at distances previously impossible, observe vehicle convoys under cover of darkness, and perform reconnaissance without alerting adversaries. Even partial visibility provided a critical edge. A single squad armed with infrared could disrupt enemy formations, identify ambushes, and protect flanks during nocturnal operations. Operational reports emphasized both tactical and psychological advantages. Soldiers described a newfound sense of control. We were no longer moving blindly. One corporal noted in a field diary. We could see them before they saw us. Commanders echoed the sentiment, recognizing that night could now be leveraged rather than feared. Yet limitations remained. The early infrared rifles were heavy, fragile, and required constant maintenance. Batteries drained quickly, often after only an hour of continuous use. The devices were sensitive to dust, humidity, and rough handling. Training was essential. A poorly trained operator could misread images, misfire, or inadvertently reveal his position. Engineers continued refining designs, and field units developed protocols to maximize effectiveness while minimizing risk. The production numbers were modest, but significant for the technology's infancy. By the end of 1944, several hundred rifles and vehicle-mounted systems had been deployed in North Africa, Italy, and select Pacific operations. Each unit represented an intersection of engineering innovation, battlefield necessity, and logistical effort. Although the infrared scopes did not turn the tide of any single battle, they symbolized a new era of night warfare and the potential for technology to reshape tactics. Beyond immediate combat, the success of Sperry's devices influenced broader military planning. Allied commanders began incorporating night operations into strategic calculations, no longer assuming that darkness imposed a blanket disadvantage. Training regimens evolved to include night vision use. Reconnaissance missions were planned under low-light conditions, and specialized units emerged to exploit these technological gains. The deployment of infrared technology also underscored the importance of cooperation between military engineers and combat units. Soldiers provided essential feedback, reporting usability issues, environmental challenges, and operational quirks. Engineers adapted rapidly, creating iterative improvements that would set the stage for post-war developments in night vision and battlefield electronics. The first operational use of infrared scopes marked a turning point. Night combat ceased to be purely reactive. The U.S. had, for the first time, a means to see where before they could not, to act when previously forced to wait, and to engage with precision that blurred the line between day and night. The battlefield, once dictated by the sun, was slowly entering a new dimension, where technology could bend darkness to human advantage. These early successes, however, were only the beginning. Full understanding of the technology's impact required comparison with the enemy, assessment of long-term strategic value, and reflection on lessons learned from both triumphs and failures. While the initial deployment of Sperry's infrared scopes offered tactical advantages, the broader implications extended far beyond immediate battlefield successes. American units equipped with night vision could conduct raids, reconnaissance, and defensive operations under darkness with a level of control previously unimaginable. Even partial visibility changed the rhythm of combat. Soldiers moved with purpose, commanders could plan offensive maneuvers, and the psychological edge shifted in favor of those who could now see the night. The Germans, while advanced in their early infrared development, faced limitations of their own. The Vamper system remained short-ranged and cumbersome, restricting its widespread deployment. By late 1944, Allied forces in Italy and North Africa had begun countering these systems through improved tactics, decoys, and flares. In comparison, American infrared development, though later, focused on practical battlefield integration and user training, ensuring that soldiers could operate effectively in varied conditions. Over time, these improvements leveled the playing field and, in certain environments, gave U.S. forces a strategic edge. Production and refinement continued through 1945. Batteries became lighter and more reliable. Lens optics were refined for clarity, and scopes were better integrated with standard infantry weapons. By the final months of the war, infrared-equipped units could carry out night operations with unprecedented coordination, although numbers remained limited. Each deployment, each successful engagement, validated the vision of those engineers and soldiers who had labored over prototypes years earlier. Beyond World War II, The legacy of Sperry's infrared systems was profound. The experience laid the foundation for Cold War innovations in night vision, thermal imaging, and battlefield electronics. Military doctrine began to incorporate the concept that darkness could be mitigated through technology, fundamentally changing tactical planning and operational flexibility. The first infrared rifles were primitive by today's standards, yet they represented a leap that would define modern warfare. Reports from soldiers and officers alike emphasized the transformative impact. A lieutenant who tested the scopes in Italy wrote that night patrols felt like a new war entirely, no longer dictated by chance or fear. Engineers noted that field feedback accelerated innovation. Lessons learned under harsh conditions informed post-war development for decades. The collaboration between laboratory science and combat necessity became a model for future military research. Strategically, the adoption of infrared vision altered the perception of night combat. What had once been an uncontrollable variable, the sun's disappearance, became a manageable operational factor. The battlefield expanded beyond daylight hours, increasing the tempo and unpredictability of engagements. Even limited success in night operations forced adversaries to adapt, influencing tactics, patrol patterns, and force disposition. Ultimately, the first American infrared scopes symbolized a convergence of human ingenuity, technological innovation, and battlefield necessity. A problem that began with fear and vulnerability, blindness under darkness, was transformed into opportunity. Soldiers gained confidence, engineers honed precision, and commanders learned that night could be contested rather than endured. The war may have continued to rage across continents, but in the shadows of 1943 to 44, a new tool was emerging that would forever change the nature of combat. This transformation leads naturally into reflection, a calm, philosophical closure that examines not just the mechanics of night vision, but its historical significance, human impact, and enduring legacy. War has always been a contest not just of strength, but of perception. In 1943, American soldiers faced the starkest reminder of this truth. The night could hide the enemy, turning every mission into a gamble. Darkness did not discriminate. It stripped the familiar from the world, leaving only fear, instinct, and the faintest hints of movement. In those shadows, lives were lost and opportunities slipped away. The invention of infrared night vision by Sperry Gyroscope was more than a technical achievement. It was a bridge between human limitation and ingenuity. Engineers transformed abstract physics into tangible advantage. Soldiers learned to trust their eyes when the natural world offered none. Commanders could plan operations with a clarity that the setting sun had once denied them. In this convergence of human courage and technological vision, darkness became negotiable. The impact of these early devices echoed far beyond the deserts of North Africa or the hills of Italy. They demonstrated that warfare was no longer bound by daylight. They sparked a lineage of innovation that would shape night combat for decades. Thermal imaging, improved optics, and modern night vision goggles all trace their roots to these first bulky prototypes. The lessons learned were not just technical, but philosophical. Even the most absolute obstacle can be overcome when necessity meets creativity. Yet the story of infrared night vision is also a story of human experience. Soldiers moving cautiously through blackened terrain, engineers poring over flickering screens, commanders weighing risk and reward. all illustrate the profound interplay between technology and humanity. It reminds us that even the coldest instruments of war are ultimately measured by the lives they protect and the decisions they enable. In the end, the night is no longer merely a veil. It became a space where human ingenuity illuminates possibility. Through the lens of an infrared scope, the unseen became visible, fear became strategy, and the darkened battlefield became, for the first time, a place where America could act rather than react. The shadows of 1943 still linger, but they also illuminate a timeless truth. Even in the darkest moments, vision, human and technological, can change everything.